I'm Ekta, and today I'll be presenting the round robin scheduling algorithm. And this presentation is the part of the operating system concept source, and I'll be explaining the idea behind the algorithm, how I implemented it, and how different quantum values affect the system performance. And moving on to the introduction, what is CPU scheduling? CPU scheduling is the method used by the operating systems to decide which process should run on the CPU. Since multiple processes compete for the CPU time, scheduling helps improving the waiting time, turnaround time, and overall responsiveness. And why round robin? I chose round robin because it's simple, fair, and used widely in time sharing systems. And it works well when many users or programs are running at the same time. Um, Overview. Round robin works by giving each process a fixed time slice called a quantum. All processes wait in a circular queue. If the process finishes its within, if the process finishes within its quantum, it leaves the queue, and if it doesn't, the remaining burst time is pushed back into the end of the queue. This keeps cycling until every process finishes, and the main goal is fairness. So every process gets equal and repeated access to the CPU. Next, objective. The objective of my assignment was not just to explain the round robin but also to design and test it. And I implemented the algorithm in Python and experimented it with the four quantum values. I measured waiting time, turnaround time, and the context switches. Then I compared the result to determine which quantum performs the best for the chosen dataset. Next, this slide shows the inputs used in testing the algorithm, and I worked with the four processes and assigned the arrival times and the burst times. Then I tested round robin using four different quantum values 2, 3, 4, and 6. Using the same process set for all the tests um, helps us compare the results fairly. Implementation. These are the steps that I follow to implement the algorithm. First, I read the process information. Then I set the quantum. I used a ready queue to simulate how the operating system schedules the process. And then after that, each process is executed for one quantum. And if still has some time, if it still has some time left, it goes back to the queue and I calculated the waiting time and turnaround time for the every process, and we repeat the same steps for all the quantum values and will compare the results. This slide shows the output generated by my code. It displays the waiting time and turnaround time for each process based on the quantum used, and it also shows the context switching, which is how many times the CPU switches between the processes. This output acts as the base for my comparison in the next slide. This table compares the key metrics for the quantum value of 2, 3, 4, and 6. We can see how the quantum size affects the performance. Smaller quantum values lead to more context switching and higher waiting time. As the quantum increases, the waiting time and turnaround time improves, and this table helps us identify which quantum works the best. And in our case, the quantum 6 works the best. Analysis. The analysis shows that a very small quantum increases the overhead because of frequent context switching. Medium quantum sorry, medium quantum gives balanced performance. Larger quantum reduces the switching and improves the waiting time. But if the quantum becomes too large, the algorithm starts behaving like the FCFS, that is first come and first serve. From the results, the quantum value of 6 gives the best balance for this dataset. Conclusion. To conclude, round robin is a fair and efficient scheduling algorithm for time sharing environments. The quantum value plays a major role in the performance. For the data sets I used, the quantum of 6 provided the lowest waiting time, lowest turnaround time, and fewer context switches. So, choosing the right quantum is important for optimizing round robin's performance. That completes my presentation. Thank you for listening. I'll be happy to answer any questions. Thank you.